Yes. So welcome all. Today we will discuss the free radical reaction involving some novel catalyst or reagent. One of them is CCl4 carbon tetrachloride. How carbon tetrachloride can react the different precursor and it bring out the addition reaction, or we can say how CCl4 can be added to multiple bond containing alkenes or alkynes. Remember, CCl4 is a very less reactive compound, but by initiating some free radical changes, CCl4 can be made, can be activated like this. In the presence of initiator, say benzoyl peroxide, or many types of initiators are also available, which can be used to activate CCl4. These initiators react with CCl4 when they form this reactive species, this CCl3 free radical, and in this way CCl4 addition can be takes place. The example is before you, this compound containing double bond. If you add CCl4 across this in the presence of certain initiator, say benzoyl peroxide, so two products are formed. The first direct product is addition of CCl4 across the double bond. This should be the product. And the second is this one which is formed by the generation or arrangement of free radical in this molecule. So how to write the mechanism or how to understand this? Let us go for mechanism. In this, we can see that initiator first of all form its radical reactive species that will attacks or reacts with CCl4 and converts CCl4 into reactive free radical, that CCl3 radical. This CCl3 radical then react with olefin or alkene. Here it is given before you. By homolytic addition, there is a addition of CCl3 radical according to Markovnikov rule, we can say, which leave the most stable radical free radical. This free radical will be attacked by the another CCl4 molecule, and that will give you the simple addition product and again regeneration of CCl3 radical. This CCl3 radical further attacks a new molecule and same process continues. In this way CCl4 and this alkenes consumption continues till the complete consumption of one of the reactor, and only then reaction will stop. This is the simple additional product. What is another product that is possible from this? That is what? See, this is the same, this and this same. So now see what will happen in this. There is a homolytic cleavage. You see, there is a homolytic cleavage. This cleavage takes place, that will give you such type of radical. Again, one radical. You can see this bond breakage will generate one radical here, one radical here, and there is a formation of bond, and this radical is methyl groups. Now this will react with CCl4 molecule, and again followed by the radical mechanism, and this is the product which is formed this reaction. Let us go for the another reaction involving radical mechanism. There is a reaction of lead tetraacetate. Lead tetraacetate is a versatile reagent for many types of reaction in organic chemistry and organic synthesis. The most important point is when there is an involvement of LTA, lead tetraacetate. Remember, saccharization is a very common reaction involving lead tetraacetate. and this takes place by the abstraction of delta hydrogen. We know alpha hydrogen, beta hydrogen, gamma hydrogen, and delta hydrogen. See, the example is there before you of an alcohol, butyl alcohol, and butyl alcohol. These n butyl alcohol have how many types of carbon? You see, alpha, beta, gamma, delta. It has a four types of carbon: alpha, beta, gamma, delta. You can see. So delta abstraction takes place. You will get this product. What is the mechanism? Very simple mechanism. Lead tetraacetate undergo free radical mechanism. Heating will bring out the changes in this OH bond, homolytic cleavage, and this type of intermediate would form. Then that intermediate we can write like this. This alpha, beta, gamma, delta, alpha, beta, gamma, delta, alpha, beta, gamma, delta hydrogen cleavage takes place, and this H shift here, and this PbOC shift that side, and after that the final stage is what? Again cleavage from this side, and sacralization takes place. We can directly write sacralization also from this to this, but this is the most reactive intermediate which form that will collapse into this tetrahydrofuran THF. So very limited reactions are there involving lead tetraacetate. See one more example. There is a cyclooctanol. It is a cyclooctanol. You see there are eight carbons. 1, 2, 3, 4, 5, 6, 7, etc. When you react this with the lead tetraacetate, so there are four types of carbon again: alpha, beta, gamma, delta, and it continues further. And you see when you react heating, it's a heating, okay. It's heating is there. On heating in the certain solvent, this lead tetraacetate bring out this acylation by the abstraction of delta hydrogen. This delta hydrogen is abstracted from this octanol by lead tetraacetate, and you get this compound. Mechanism is same. Let us go for the next molecule, reactions by tributyltin hydride. How the reactions of tributyltin hydride takes place. We will discuss this, we will try to understand this. Okay. So now remember this tributyltin hydride, the structure is here before you. There are three butyl groups and central atom is 10 and hydrogen is attached to this. So it is a reducing agent in combination with AIBN, isobutylene nitrile is a reagent initiator, or in presence of light, this tributyltin hydride converts the organic halide, the alkyl halides, into corresponding hydrocarbon. It's one of the primitive stage or primitive reaction. But later on, many reactions has been discovered by which involves the tributyltin hydride and its reaction. So, what is the mechanism actually followed by tributyltin hydride is? What is the mechanism? This is what the first step is initiation, which involves the generation of reactive tin hydride or tributyl tin radical by AIBN, and then that radical will react with alkyl halides, remove halogen and generate alkyl radical. That alkyl radical further reacts with the this one reacts with any alkene. An addition reaction takes place, and that addition reaction again generate the new radical, which is again reacts with next second molecule of tributyl hydride. Transfer of hydrogen takes place, and final product with the formation of again reactive intermediate. This reactive intermediate is nothing but like this. This reactive intermediate reacts with another alkyl halide and again generate this one and this one. This alkyl halide reacts with the olefin, and again that olefin after addition of this alkyl halide radical generate another radical, new radical, that is that abstract an hydrogen from this butyl tributyl hydride reagent, and this continues, this chain continues. This is a very simple and widely accepted mechanism how tributyl hydride functions. We'll go for example. See, the left side is what? The chlorocyclohexane is alkyl halide, and its reaction with this alkene and in the presence of tributyl hydride, that is the product. What is the mechanism? Same. AIBN is used as the initiator that initiate the reaction, generate the radical. That radical bring out free radical reaction in the alkyl halide, and there is a formation of cyclohexyl radical and this tributyl chloride. If you are using bromine, bromide, and this cyclohexyl radical reacts with alkene, and that alkene undergo homolysis cleavage, and addition takes place. That free radical generation takes place. This free radical react with another molecule or second molecule of tributyl hydride, abstract hydrogen, and generation of tributyl radical. That will attack next molecule, and in this way this reaction continues as chain reaction. Go to next example. Again, very simple concept. This is the molecule before you containing two types, two reactors or two functionality. Like this, in this we have two different functionality. One is alkyl halide, another is alkene. But here both are here. Alkyl halide is also there, and double bond alkene is also there. This addition is always possible by the radical mechanism using this tributyl. So what is the expected product? What product we can expect? What is the product we can expect in this reaction? What product we can expect is, so we can proceed. We can proceed for the mechanism. So see the mechanism. First of all, initiator, we can use radiation, we can use AIBN, we can use many are available. The initiator function is to initiate the reaction. How? By inducing the generation of free radical. You can see here. This initiator break this SNH bond and generate this radical. That radical will react with this alkyl halide or this particular precursor, and it will attack here Br bond, CBr bond, and that will undergo into what? Homolytic cleavage. Definitely formation of radical takes place. That Br gone with this one. This radical is formed. Now this radical initiates certain changes. How? This double bond undergo. This double bond undergo. See, this double bond undergo homolytic cleavage. Generation of radical at this side and this side, and formation of this bond. Without any hesitation, you can directly connect the radical and form bond formation. Hope you don't have any objection up to this reaction, up to this step. Very simple approach, very creative approach. Now what is next? This radical, what it will do? It will react another molecule of this tributyl hydride, abstract proton or hydrogen in fact, and that will give you final product. And again, generation of tributyltin hydride radical that react to next molecule. This one molecule is converted totally into this product. So product is this one. So final product is this one. Remember, the final product is this one. You can write here, no? You can write here, but a very simple approach. Don't no need to disturb any other bond, any other functionality. Our target is what? Our mechanism is target oriented. Go for next molecule. So these are the practice questions for you all. So all these we have done already. Okay, so these 4 reactions, complete the reactions and write the product mechanism also. So what is the product you should write? This is the hydrogen peroxide. It is also hydroperoxide. This is what NBS, function of NBS, where the bromination takes place. Write the product and write the mechanism. Similarly, this is again, you should write the mechanism how this will form. So these are the simple method. Terminal alkynes become non-terminal alkenes. Terminal alkenes become non. These 4 examples. You have to solve these examples. Okay. Yes. So do this all of you. Okay, right. So now, how this will takes place? So this 4th one, these 3 you have to do, all of you. This 4th one I will try to explain before. See, this is the very excellent reaction. Okay, interesting reaction. See, out of these 4 reactions, we have done this, yes or no? Yes. We have done this. This also we have done. You can watch the videos and you can do this. Similarly, this also we have done. Only this is what the particular reaction. But these 3, it is assignment for you all. You have to submit this, okay? This week assignment. This is the assignment of this week. You all of you do this and submit it. Okay, right? Now see how this will form. Let us go for the mechanism. First of all, this reagent undergo homolysis and generation of this radical. That radical abstract hydrogen from this hydrogen, allylic hydrogen. Okay, that allylic hydrogen will be generating this radical, allylic radical, which is very stable, undergo into resonance like this. That's all. Finish. And then Cl radical, this Cl radical attacks here and that will form the final product. So by having the ideas of different reactions which involving different steps in the radical reaction mechanism, one can easily write the product, and one can easily predict the fate of any chemical reaction which involves the radical generation. See, fine.